So whenever we put a sample of any element or a compound in a mass spectrometer is basically responsible to tell us how many isotopes are there of any element and what are their masses and their relative abundances. Relative abundance, or it is also known as percentage abundance, is basically tells us that for example, if any element has two or more than two isotopes, so it tells us that the proportion of each isotope present in that particular element is given in the form of percentages. For example, if we see the mass spectrum of neon element, here we can see it's 3 peaks. Here we can see we have 3 signals, or we call it peaks. Here we have 3 peaks for neon isotopes. One at the mass number 20, one at the mass number 21, and the third one at the mass number 22. So a neon element has 3 isotopes, one with the mass number 20, one with the mass number 21, and the third one with the mass number 22. And their relative abundances, or the percentage abundances of each isotope, is 90.9% for neon with the mass number 20 and 0.3% for the neon with the mass number 21 and 8.8% for neon with the mass number 22. So how do we find the average mass of all these isotopes? We use these percentages to find the average mass. Basically, we have to find the average on the basis of these percentages. We will take the mass of neon 20 as 90.9%. So 90.9% of neon 20 plus 0.3% of neon 21 plus 8.8% of neon 22. So how do we solve percentage? We divide it by 100, divided by 100, 90.9 over 100 into 20 plus 0.3 over 100 into 21 plus 8.8 over 100 into 22. When we're going to solve this, we will get the average mass of all of these isotopes of neon. And that average mass is known as relative atomic mass. And these relative atomic masses are then written in the periodic table. So can anyone tell me what is the value coming out for this neon? 90.9 into 20 plus 0.3 into 21 plus 8.8 into 22, all divided by 100. Is coming out to be 20.179. So if we just round it off to 1 decimal place, that would be 20.2. And in the periodic table, in order to represent a neon element, we would write this mass. We have to represent a neon element. We could have taken only one isotope of neon, but that would be unfair with the other isotopes. So instead of just writing the one isotope, we take the average of all the isotopes of neon. So if you see the periodic table here, you can see neon has a relative atomic mass of 20.2. So now in your A level, you will have to write the atomic masses up to 0.1 decimal place. But if you recall from your grade 11, you are just used to write neon as 20. But now we will write all the relative atomic masses up to 1 decimal places. If you see most of the elements, they have their masses in decimal up to 1 decimal place. It means most of the elements have isotopes. Their quantity may be 2 or more than 2. So it depends. Getting my point? Sometimes we call it average relative atomic mass. Sometimes we just call it relative atomic mass. We will study more about relative atomic masses in the chapter moles, but for now you should just be able to just practice enough that you should be able to calculate the relative atomic masses if your mass spectrum is given. For example, if you see the mass spectrum of this element is not named, but if you just see the peaks on the mass spectrum, we have 1, 2, 3, 4, 5 peaks. It means this particular element has 5 number of isotopes. You can also read out the masses of each isotope. The first isotope has a mass number equals to 70. The second isotope has a mass number equals to 72. The third isotope has a mass number equals to 73. The fourth isotope is 74. And the fifth isotope is 76. The percentages are given at the top of the peaks. although you could have read it from the y-axis, but again, the scale of y-axis is so small that it would be impossible to read out the value as 20.6. So usually they give the percentages written over the top of the peaks. So now it's just your simple calculation. You just have to take the average from these percentages, and that would be your relative atomic mass. Do I need to just show it how to solve this question, or you guys can do it by yourself? Guys, be active. Oh, you need it. Okay. So first isotope has a mass number 70. So its percentage is 20.6. So we're gonna take 20.6% of 70 plus second isotope has a percentage abundance of 27.4. 27.4% of 72 and 7.7% of 73, then 36.7% of 74, and finally we have 7.6% of 76. Got it? Is it clear now? Or you could have just written it like this, because 100 is present in all the terms. So you could have just taken the LCM. I mean, just from the start, if you just multiply their percentages by their relative atomic masses, that would have been fine too. Because if you just directly use the calculator, you can use the fraction key in your calculator. In the numerator, you can just keep multiplying their percentages by their masses, and in the denominator you can just divide it by 100. Sorry, why I'm keep saying 1000. It is 100. So you can just divide it by 100. For all the values you could have just written 100. So that becomes easier to solve, because you could have done just this directly in your calculators. Are we clear so far? Should we move on? Moving. Okay. Now, if you see the questions from the past papers, they are quite simple. In the question, it says the mass spectrum of an element is shown. You can see the number of peaks. These number of peaks actually represent the different number of isotopes. What is the relative atomic mass of this element? So I'm giving you the chance to solve this question. Here, they haven't given you the percentages, but their percentages you can clearly read out from the graph. For the first isotope, this is 60%. For the second isotope, it is below 20. So each small box is representing 2%. So it must be 18%. It is 18%. And I think if you guys can do it on your own, that would be wonderful. I can just give you 1 minute for this. Okay. Try. Never surrender. And you guys should accept a test on coming week, right? As we are done with this chapter, so obviously you will be tested for this chapter. Okay. The answer is C, 91.2. All of you are giving the correct answer. Pike and Sarah. Sarah has given C, Rida C, 5. You are left. I'm moving on, okay? Safe. Okay, this question. The diagram shows a mass spectrometer. We have learned this number of stages. I would recommend that if you guys can make your notes from this question, if you can take the reference of this question number, that would be very good. You can just incorporate this question in your class notes. It's a good question. Here they have given you the diagram of a mass spectrometer. You won't be asked to make a diagram of a mass spectrometer, but you should know the stages involved in mass spectrometer. The first stage is ionization, right? After ionization, you have to deflect the charges. So after ionization, we have deflection. After deflection, we have detection. And before deflection, we have acceleration, of course. Okay, I'm expecting answers. Sarah, Fike. Okay. Which processes occurs in region R? Clearly, region T is your deflection, where you can see the particles because the dotted line they have drawn must be showing the path of the particles. Clearly, region T, deflection is taking place, right? It is tough to identify between R and S, but if deflection is taking place in region T, before deflection, detection must be taking place at the detector. They haven't given any symbol for detection, but obviously when the particle reaches the detector, that is the phase for detection. Before deflection, it has to be acceleration. So S must be acceleration, right? And before acceleration, we must have R should be having ionization. And ionization is done by removing the electrons. So process in region R is basically ionization. Now let's see in which option he is talking about ionization. In option A, is saying the sample is vaporized using a heater. So sample is always vaporized before the ionization. Everything that you are entering into the mass spectrometer must be in the vaporized form. So if you just want to add one more step before ionization, everything has to be converted into the vaporized form. If a sample is already in the gas form, just like we were doing for chlorine, chlorine is already gaseous form. So we are not supposed to vaporize chlorine. But let's say if you are entering any metal into the mass spectrometer and if it is in the solid form, you have to heat it to convert that solid state of that metal into its gaseous state. That's what vaporization is, right? So first you have to vaporize everything, then you ionizes, then acceleration is done, then deflection and detection. I was actually tracing my processes from rightmost side to the leftmost side. I can clearly say that T is the deflection. Before T must be acceleration and before acceleration must be ionization. So it cannot be vaporization because vaporization must be before R. And they haven't labeled anything regarding vaporization, but it should be done in this compartment. B says the electrons are removed from the molecules or atoms and positive ions are formed. That's what ionization is. So B must be correct. C says electrons are added to the molecule. Whenever you are adding any electron to any molecule or atom, it will form a negatively charged ion. In mass spectrometer, we have already established that we always remove the electron to make a positively charged ion. So option C is incorrect. Then for option D, ions are accelerated by an electric field. So acceleration will happen after ionization. So S is your acceleration. That's why I'm saying, because this particular question incorporates all the concepts of mass spectrometer. So it's better if you write this question in your notes. Just give it the reference number for this question. Let me show you. It's from, this is the paper. Okay, I haven't written the year number, but I will attach this question in your class notes. You will get it. The year number was written in the file. That's why I have missed it. Okay, now the part B says which statement is correct for region T. So for region T, ions with a greater mass have smaller deflection. Remember what we discussed, that if a particle is heavier, if it has a higher mass, it will be deflected at a smaller angle, right? So ion with a greater mass have a smaller deflection. Isn't it correct? B says ions with a greater mass have greater deflection. This is wrong, because angle of deflection, as we were studying just yesterday, angle of deflection in a mass spectrometer basically depends upon charge. If the charge is greater, the angle of deflection would be greater. But if a mass is greater, the angle of deflection would be smaller. That's why B is wrong. C says ions with a greater charge have a smaller deflection. That is incorrect, because ions with a greater charge will have a greater deflection, not a smaller deflection. The smaller is wrong over here. Getting my point? D says ions are separated up by magnetic field. See, deflection can be done by electric field, as well as deflection can also be done by magnetic field. Because whenever a charged particle passes in an electric field or magnetic field, it is always deflected. If you just recall your grade 11 physics, when a charged particle used to move in a magnetic field, it is used to be deflected. And the direction of the deflection of the charged particle you used to found by Fleming's left-hand rule. If I am right, the direction of the deflection of a charged particle can be found by using Fleming's left-hand rule. Right-hand rule is used for something else, the left-hand rule. So if a charged particle passes through electric or magnetic field, it is deflected. So ions are separated by magnetic field. Actually, ions are not, sorry, it is ions are speeded. It's not separated, I'm sorry, it is speeded. The ions are not speeded by a magnetic field, but ions are deflected, or it can be deflected by a magnetic field. It can also be deflected by the electric field. But ions are accelerated by electric field. If you say how ions are accelerated, they are always accelerated by electric field. What sort of electric field? Let's say if the ions are positively charged in the mass spectrometer, so what we can do is we can take a cylindrical anode. What is a cylindrical anode? Let's say if we have this book, and if I just fold it like this, if I just make a cylinder of it, and if we have this, if we make this cylinder positively charged, so the charged particle when enters, I hope you guys can see my video, when the charged particle enters here, so what happens, they experiences force, equal force from all the direction. So they cannot go to the walls from anywhere. So they will stay in the center. In fact, they will not just stay in the center, but they will be pushed in the forward direction. So they are always accelerated when they are passed through a cylindrical anode. Usually we take cylindrical anode, we could have taken cylindrical cathode as well. We have just a cylinder, and we can just make it positively charged by connecting it with the positive terminal of a battery. Got it? So far, so good. Don't be scared from my death note. Should we move on? Okay, let me show you one more question. I'll do this question, but in a while. Okay. Coming back towards the concept of mass spectrometer, Yesterday, we just studied how any element, if entered into a mass spectrometer, would give you a mass spectrum. But let's say if you are entering a chlorine molecule, let me just show you the real mass spectrum of chlorine molecule. The real mass spectrum of chlorine molecule would look something like this. It has different peaks. We were expecting that a chlorine element has only two isotopes. So one with the mass number 35 and one with the mass number 37. But whenever you run a mass spectrum of chlorine, you actually get more than two peaks. And these other peaks are due to the chlorine molecules. So if you could just make a heading, molecular ion peaks. Yes. Okay. When we are entering a chlorine molecule into a mass spectrometer, we were saying that it is bombarded with a fast moving electron, due to which some of the electrons from the shared pair may be knocked out from this molecule, due to which the bond between these chlorine atoms will break down, right? If the shared paired electron is knocked out, obviously the bond will break down and we will get a chlorine positive ion. And this chlorine positive ion may be having a mass number 35 or it may be having a mass number 37. It may be different from molecule to molecule. But there is also a possibility that these fast moving electron just does not knocks out the shared pair of electron. Maybe in some molecule, these fast moving electron just collides with the lone pair of electrons and just knocks out one of the lone pair of electrons. When it just knocks out a lone pair of electron, we will get Cl2 with a charge of +1, right? Because this time, if the shared pair electron is not knocked out, the bond won't break. The molecule will stay intact. But as one of the electron has been knocked out, so this complete molecule will become one electron deficient, due to which it will get a charge of +1, because number of protons are same in the nucleus of both the chlorine atoms. One electron has been knocked out. It means the molecule would become one electron deficient. So there must be a positive charge. I know there is always a possibility that why we are just saying one electron is knocked out. Isn't it possible that maybe more than one electron is knocked out? It means a mass, in a mass spectrum, we can also get a charge of 2 positive or a charge of 3 positive. But obviously, and we are getting these types of charges. But whenever we are going into the deflection phase, before going into the deflection phase, we just filter out these charges. Because if we just allow these charges to pass through the mass spectrometer, what happens when we are going to find the charge to mass ratio or mass to charge ratio, then the values would be very different. Because for now, if we just consider all the charges with +1, so their numerator would just give you the ratio of this value. The value for this ratio would just be equals to the mass. Because if we just keep the charges +1, that would be quite simpler. So we actually filter out all other ions with charge other than +1, like +2, +3. We just stop these charges before the deflection phase. And we just allow all the particles with a charge of +1 to enter into the deflection phase. This concept, this particular knowledge you are not supposed to know, but you just have to know that only +1 particles are allowed to pass further through the mass spectrometer and they will reach to the detection phase. So my concern is, if you have a molecular ion, this is known as molecular ion, of course, because Cl2 is a molecule and it has an overall charge. So we would call it a molecular ion. So won't this be deflected? Obviously, this will also be deflected with Cl positive ion. Hence, let's say if we have two isotopes of chlorine, it means we will have one peak due to Cl positive with the mass number 35, the other peak due to Cl positive with the mass number 37. So we were already getting these two peaks. But what if this molecule reaches the detector? So won't it give any extra peak? Obviously, it would give its own peak, but its peak's mass would also differ, because let's say if in this particular molecule, both of these chlorine has a mass number 35. Both of these chlorine atom are 35 isotopes. So the mass of peak would be equals to 70. What you say? It should be right. Now what if both of these peaks, let's say if we have a molecular ion peak, but both of these chlorine atoms are not equals to 35. One of the chlorine has a mass number 35 and the other chlorine has a mass number 37. So the total mass of this peak would be equals to 72. And is there any other combination? Yes. If in this molecule, if both of these chlorine atoms have a mass number equals to 37, then we would get a peak with a total mass of 74. The charges are all positive one. So mass to charge ratio, in a mass to charge ratio, mass will only change in the numerator. The denominator will stay same. So what do you expect? How many total number of peaks should be present in a mass spectrum of a chlorine? There should be 5 peaks. And if you see the mass spectrum of chlorine, yes, we have 5 peaks. Let me show you actual mass spectrum of chlorine. Here we have 5 peaks. The peak with the chlorine mass number 35 represents a chlorine ion with the mass number 35. The second peak represents a chlorine with the mass number 37. If you see the relative abundance, they are in the 3:1 ratio, 75-25. I was saying that if we find the mass, because if you see the x-axis of mass spectrum, this is not just mass, this is mass to charge ratio. But we are just reading the mass from the x-axis. Although it is not just mass, it is mass to charge ratio. But if we just compare all of these peaks, the only mass number is changing. For chlorine 35 is 35, the charge is positive 1. For chlorine 37, the mass is 37, the charge is still positive 1. For the peak with the mass number 70, the charge is 70, charge is plus 1. For the peak with the mass number 72, charge is positive 1. So denominator is same for all of these peaks. And if you are dividing anything by 1, the value would be equals to the numerator. So we can say the mass to charge ratio is basically equals to the mass of that particular peak. Got my point, Rida? Okay. So here we have 3 more peaks. Obviously, if you just running the mass spectrum of chlorine for the first time, you would just try to identify these chlorine as 3 other different isotopes of chlorine. How would you know these are not different isotopes of chlorine? Because when you see their mass number, the first isotope has a mass number 35, the other isotope has a mass number 37. They have written this mass number on the top of the peak. Now here it is not the percentage, right? So can a chlorine element have any other isotope with a mass number 70? Do you think it would be possible for a chlorine atom with number of protons 17? It makes sense that if a chlorine atom has 17 protons and 18 neutrons. And again, it still makes sense if a chlorine atom has another isotope with 17 protons and 20 neutrons. But does it make sense that, let's say if we consider this as one of the isotopes of chlorine, how would you know that it's the molecular ion peak? Let's say if you have known nothing about chlorine, you have never known that chlorine has 2 isotopes. The first person who performed the mass spectrum of chlorine, did he know that chlorine has 2 isotopes? No, he was just started performing the mass spectrum of chlorine and he just saw 5 peaks. So his first reaction would be a chlorine element has 5 isotopes. But if you just see it clearly, the 2 of the isotopes has a mass number 35, 37, and the third isotope, if given the mass number 70, do you think it makes sense that the number of neutrons in the third isotope should be equals to 70 minus 17, which is 53? We can just comprehend that number of neutron increases by 2, it's okay. But number of neutrons from 53 till 18, it's 35 more neutrons. Do you think this 17 protons are able to hold up this much number of neutrons? Element with such a big difference between the protons and neutrons can never stay stable. It will keep on disintegrating. And that's what happens with the radioactive elements. So chemist, he should come up to the conclusion or come up to the realization that this cannot be the third isotope of chlorine, because the third isotope cannot have this big of a mass. So it means he just realized that, oh, it's a molecule of chlorine. Here we have two atoms of chlorine. So this peak at the mass number 70 must be the molecular ion peak with both the isotopes of chlorine with the mass number 35 in it. And then if we see the other two peaks, then that would have made more sense that the second molecular ion peak have one of the chlorine with the mass number 35 and one of the chlorine with the mass number 37. Similarly, the third peak must be also a molecular ion peak with both the isotopes with the mass number 37. Got it? Now, if you see the ratios between these three peaks, molecular ion peaks, if you see the ratio between the two of the peaks of chlorine isotope with the mass number 35 and 37, that is 3:1. And 3:1 would give us 75% and 25%. But if I just ask you to find the ratio between the other three peaks, you can just take a meter rule, or you can just like measure the heights of each peak and take the average, or take the simplest ratio. But what if I just ask you to find their ratios by using the peak of the other two isotopes? Let's say we have chlorine with a mass number 35 and we have chlorine with the mass number 37 and we have Cl2 with a mass number, or let me just write it like this, two chlorine atoms with bonded to each other, so it's a molecular ion peak, one with the mass number 35, the other isotope also with the mass number 35. So this is 70. And then we have a molecular ion peak in which both the chlorine atoms are of different masses. One is 35 and the other is 37. So this is 72. And never forget to write the positive charge over the peak. Otherwise, it cannot be counted as a molecular ion peak. And then the third isotope, again a positive charge, but these two isotopes are having the mass number 37. So the total mass would be 74. The first two isotopes, the chlorine isotopes, are in the ratio 3:1, right? So if you just find the percentage or a fraction, or rather would we say a probability of having, okay, you guys know what probability is. If I say what is the chances of having a chlorine with the mass number 35, so this is always 3/4. And what are the chances of having the chlorine with the mass number 37? This is 1/4. So if we have a molecular ion where we have two chlorine atoms, so what would be the chances of having both the isotopes with the mass number 35? The first atom of chlorine with the mass number 35, its probability is 3/4. And again, the second isotope with the mass number 35 is again 3/4. So it would be 3/4 into 3/4. That would give you 9/16. I just need you guys to grasp this. Take your time. Let me know if it is clear up till now. Let's Rayan, Paik, Sarah. All clear? Okay. Now, what about other elements? What about chlorine, other molecular ion peak, or any other element except chlorine? Sarah, what are you actually asking? Any other element? Yes, for any other element, if they give you the mass number, and if they give you the relative abundances, then also you can also find about it. We will take another example of bromine element. So for chlorine, and of course you're not supposed to remember this. I mean, you should know the working mechanism of this. How are we actually doing this? But for this, the relative abundances would be given. But I would highly recommend that you should always remember for chlorine and bromine. But this would be given to you that they are in the ratio 3:1. From then onwards, you can just do your calculation. So for the other two, for the second molecular INP, if the first isotope of chlorine in this molecule is with the mass number 35, so chances of it or probability of this isotope would be 3/4. But the other isotope has to be 1/4. Right? I hope it clears. But there is a catch. We are saying that the first isotope is 35 and the second isotope is 37. What if first isotope is with the mass number 37? The second isotope is with the mass number 35. This is also giving you the same mass. So the chances of having a molecular ion peak with the mass number 72 is actually not just due to this molecule, but this is also due to this molecule. How would you find its probability? It should be equals to 37 is 1/4 and 35 is 3/4. Do you remember those questions from your mathematics? Like, for example, if we have a box of balls of black balls and red balls. Let's say if we have a box with some black balls and some red balls. Let's say we have 4 black balls and 6 red balls. So what is the probability of picking out 2 balls? The one should be black and the other should be red. So they are giving you this sequence, like first ball has to be a black, the second ball has to be a red. But what if I say what is the probability of picking out 2 balls, one black and one red? I'm not saying that in the sad order. I'm not saying you have to pick a black ball first. I'm just saying just pick out 2 balls. One should be black and the other should be red. So you can just do it by picking a black ball first and then red, plus a red ball first or then black. I'm just hoping that you guys have the idea of probabilities. Do you? Okay. What about the third molecular entity? It should be 1/4 into 1/4. It should be 1/16. If you solve this, it should be 3/16 plus 3/16. That would give you 6/16. So if we just take their ratios, first is 9/16, the other is 6/16, and the last one is 1/16. If we just multiply all of these ratios by 16, we would get 9:6:1. These are the ratio between these 3 molecular ion peaks. Let me just write it over here. It should be equals to 9:6:1. Let me give you another example, but Sarah, Rayan, and 5. Bache, do you have idea of all these things that we have done? This is what we call, or what we used to call in our mathematics as probability. And that's a tough one. At least I used to find it very tough in my mathematics. Okay, You know what? Bromine element also have two isotopes. Bromine, one with the mass number 79 and one with the mass number 81. And their relative abundance is 50-50%. Now, if we have a molecule of bromine, so if we just enter the sample of bromine into a mass spectrum, we can get one peak with the mass number 79. We can get the other peak of bromine isotope with the mass number 81, right? But we may also get the molecular ion peaks. Like if the bond between these bromine atoms do not break, so we will get a molecular ion peak, one with the mass number 79, both the isotopes with the mass number 79. So it would be equals to 79 into 2 should be 158. And there is also a possibility that in this molecular ion peak, one of the isotope must be having a mass number 79 and the other must be having a mass number 81. Or we can also say it like this, that the first isotope must be having a mass number 81 and the other isotope must be having a mass number 79. In both the cases, the mass of the peak would be same. This is equals to 160. And if you consider the third peak with both the isotopes having the mass number 81, so it would be equals to 162. So if we see the mass spectrum of bromine isotope, on x-axis we have mass to charge ratio, on z-axis we have relative abundance. So for two isotopes of bromine, their peaks would be equal in height because the relative abundance is just 50-50%. It's 79 and 81. But again, we would be getting a peak at the mass number 158, which is like obviously so obvious that this cannot be the third isotopes of bromine. It should have been the molecular ion peak, right? Would the size of all of these molecular ion peak would also be equal? Do you think these molecular ion peaks, because when the detection happens in the mass spectrometer, it is done on the basis of the number of isotopes that are coming. In a chlorine 35 isotopes signals were coming more as compared to the chlorine 37 isotope. For example, if we have a detector and if the detector just detects like out of 1,750 signals were getting due to the chlorine with the mass number 35 and 250 signals were getting due to the chlorine with the mass number 37. That's why we were able to find the relative abundances, that we have got total of 1,000 signals. Out of those 1,000 signals, 750 signals are due to the chlorine with the mass number 35 and 25% of the signals, that is 250 signals, are due to the chlorine with the mass number 37. And that's how we just realized that relative abundances must be equal to in the ratio of 3:1. Similarly, if we just enter the sample of bromine in a mass spectrometer, so both of these isotopes have equal masses. Both of these isotopes have equal percentages. And how we came up to know that, because when we were getting the detection or signals from a bromine element, we were getting two signals, one with the mass number 79 and one with the mass number 81. So the number of isotopes or the number of signals that we were getting for the bromine with the mass number 81 was equal in number as compared to the signals that we were getting of the bromine with the mass number 79. Let's say we were getting 300 signals for the bromine with the mass number 81, then we must be getting 300 signals for the bromine with the mass number 79. So that's how we came to know that both of these isotopes are equal in numbers. So they must be having an equal relative abundance or equal percentages. So do you expect that the molecular ion peak should also be equal in height, or they must have same relative abundances? For that, you have to find the probability. Like for a bromine molecule with both the isotopes 79, what if I just asked you what is the probability of having a bromine with the mass number 79? It is equal, like half. 1/50% means half. So if we have a molecular ion peak where we have both of the isotopes of bromine as the mass number 79, it should be half into half. For second, it should be half into half plus half into half. For the third peak, it should be again half into half. Now, if we just solve it a little, for bromine, with both the isotopes to be 79, the ratio is 1/4. For bromine molecular ion peak, where one of the isotope is 17 and the other is 81, the mass is 160. So it should be like, if you just solve it, half into half is 1/4 plus half into half is 1/4. It would be equals to 1/4 plus 1/4. It should be equals to 2/4. 2/4 is again one, like 1/2. And for the third line, where both the isotope have a mass number 81 and is 162, is again half into half is half/4. So if you just take these ratios, it should be 1/4. If you just multiply all the values by, let's say, 4. So it would become 1:2:1. So it means if we are going to draw the molecular ion peaks, they are not having the same heights. The second peak with the mass number 160. Let me just draw it over here. Two of the same height peaks, but due to the two separate isotopes of bromine, not a molecular ion peaks. But if we draw the peaks of a molecular ion, this is our peak with a mass number 158. Then we have a peak with a mass number, like we are having a peak with a mass number 160, but its height is actually twice as compared to the height of the other two peaks. And the third peak should be equals at 162 with a height same as that of the height of the first peak. Yes. Are you getting it? This is for Br single atom, and all of these three other peaks are for molecular ions. It is for 158, 160, and 162. Yes, Spike and Sarah. I know it's a difficult concept. You have to revise it again. And obviously, they won't just actually, as per specification, you were just supposed to remember the relative heights of these peaks. If you just can remember these heights for chlorine, that is okay. You're not supposed to remember for bromine, but I would suggest that it's not that difficult, because everything that you have studied does not included a new concept. Everything that is being used in the mathematics, we just employed it. But again, you won't be tested for this knowledge, but we just did it. You can call it a diatomic ion, but usually we call it a molecular ion. Molecular ion is the more accurate word. So if you can just remember this ratio between the molecular ion peaks of chlorine, that you have to do. But if you can just solve it, like here, because in unit 1, here you're not supposed to solve it, but when we're gonna move to the further units, ultimately in case of halogenoalkenes, yes, in that unit you will have to solve this. One way or the other, you will be studying it, but it's okay. It makes more sense with the mass spectrometer, so we have studied it now. Any questions? Sarah and Phi. I hope you guys are okay. Not panic. Okay, now you guys have to tell me if you have practice questions with you.